Okay, so we just sort of introduced the idea of the harmonic oscillator potential. It's supposed to be more realistic because any smoothly varying potential kind of looks like a quadratic potential when you're just near a minimum or something like that. So we wrote down, we first exchanged, first exchanged out K for omega, right? We said, oh, I know, harmonic oscillator is proportional to x squared. Back in 210, you wrote 1/2 kx squared as the potential energy, but the harmonic oscillation frequency omega can be traded out instead of k. So we write it in terms of omega. So this is just 1/2 kx squared, if you like, quadratic potential. And then we gotta solve this. And there are two ways. One is called the algebraic method, and that's what we're going to do first. It's actually easier in this case. The analytic method means directly looking for solutions to the differential equations. And Griffiths, spends the latter half of this chapter talking about it. We're not really going to talk about it. You're going to see plenty of analytic solutions for other potentials. But in this particular case, we already saw an analytic solution for the infinite square well. Generally, the algebraic method is only easier for the harmonic oscillator. In all other cases, you could do algebraic solutions, but they end up being way more work than the analytic solution. So it's just kind of an oddball thing that you should be aware of, just a different way of finding the solutions to the time-independent Schrodinger equation. All right, so we defined some operators that were called the raising and lowering operators. And let me write those on the board again. Right, we've got our x hat and p hat. The x operator just means multiply by x. The momentum operator means minus I h bar d dx. In the context of the time-independent Schrodinger equation, where we're looking for just functions of x, you could replace this with an ordinary derivative because it would just be acting on functions of one variable. And we define the raising and lowering operators. The plus is for raising and minus is for lowering. And they were defined as 1 over root 2m h bar omega times minus or plus I times the momentum operator plus m omega times the position operator. And you could just directly substitute these things in for those operators, but this makes it a little bit more compact there. Okay, and our goal is the following: to show that if we can generate just one solution, then to the time-independent Schrodinger equation, then we can also show, we'll prove a theorem that says that this is also a solution, but it has a different eigenvalue, different energy eigenvalue, and therefore it's linearly independent of it, right? If this solution were still a solution to the time-independent Schrodinger equation, but it had the same energy eigenvalue, we'd say, oh, it's just a multiple of psi. But if it has a different energy eigenvalue, it's truly linearly independent, and so on. We apply it twice to psi, and we get yet another linearly independent one. And same thing for the lowering operators. This is a solution to the time-independent Schrodinger equation. This is also a solution to the time-independent Schrodinger equation. And this is called a ladder of states. Oops, I put those in the wrong place. And those will exhaust all the possibilities. And so, we got to do the details now. So we're going to do some algebra with operators. And algebra means, you're used to doing things like this. If you have an expression 2xy plus 7 equals 3x, we freely move these symbols around. In other words, we'll commute, the x and the y will switch their order without thinking. We have to be very careful because, so these would be equivalent equations. I've switched the order of those two. We have to be careful because with operators, we can't always switch the order like that. We would say they don't commute. And we have to figure out if we want to switch the order of two operators, we have to pay kind of a price. And we have to learn how to pay that price and to do algebra with them. So just for example, if we have the momentum operator operating on the position operator, both operating on psi of x, right? These operators always operate on some function, right? So this means you first multiply by x, and then you take that derivative with respect to x after that with the constants out in front for the momentum operator. This is not equal to the position operator followed by the momentum operator operating on psi of x. And that's because when we substitute in there, here we have a minus I h bar d dx of x times psi of x. And over on this side, here I'll put a question mark so we'll see if they're equal. We would have x times minus I h bar d dx of psi of x. And the reason they're not the same is because here I have to do the product rule, right? So I get two terms. Derivative of x with respect to x, which is 1 times psi, plus x times the derivative of psi with respect to x. And only one of those terms is what appears on this side. We get an extra term on this side from the product rule. All of these derivatives, the operators we're using, operate on whatever's to the right. So if you see a couple of operators stacked up, this one operates first, and then this one operates on the result of that. And like always with derivative operators, they operate to the right. So when we can't just willy-nilly reverse the order, if these orders aren't the same, there's something called the commutator, which shows exactly how the operators don't commute with each other. So the definition of the commutator of two operators, a hat and b hat, is defined to be this. It has this symbol. You put in square brackets a comma b. And what that means is just a shorthand for a hat b hat minus b hat a hat. So this is an operator by itself, right? Showing that it can be written explicitly as an operator over there. If the two operators commute, if I can switch their order willy-nilly, then the right-hand side would be 0. So the commutator is 0. It's a 0 operator. It just multiplies by 0 if the operators commute. But if they don't commute, then, oh, and I'm sorry, I'm forgetting to unshare. No, this is good. It is unshared. Need to pin my video. So let's see a specific example of this. So here's an example that's in the notes. Find the commutator between the position operator and the momentum operator. And here's how we do it. We don't just leave the operators sitting by themselves because you'll surely forget to take something into account. What we do is always let them act on a function of x. So what this means is calculate x hat p hat operating on a function of x minus p hat x hat operating on a function of x. And when we simplify that out, so we got to substitute in the formulae for the operators. When we simplify it out, we'll see it's equivalent to something operating on f of x, and that something will be the commutator. Okay, so let's write this out. The position operator just means multiply what comes to the right by the variable x. The momentum operator is minus I h bar d dx. I've replaced it with an ordinary derivative because what it's operating on is just a function of x. Okay, so that operates. You know, I could simplify this. I can always commute constants and variables, so I could bring this out in front. Minus I h bar d dx. That's the momentum operator operating on the position operator operating on f of x, and the position operator just multiplies whatever follows by the symbol x. Okay, so let's simplify this. There's not really much simplification you can do. I could bring the minus IH bar out front and put the x right there. But this thing right here, I could simplify as plus IH bar. I have the derivative of x with respect to x times f of x. Sorry, I forgot my derivative. Df dx. Plus the second part of the product rule will be plus IH bar times x df dx. Oh, I'm doing them in the wrong order. Okay, so there we go. X times df dx plus dx dx, which is 1, times f of x. I think I got that right. All right, so once I simplify that out, and that includes this minus sign here, notice that this term right here is exactly opposite of this term right here, once I commute the x with the constant there, which we're always allowed to do. So this cancels this, and so this whole thing simplifies down to IH bar f of x. So what we found is that x hat p hat operating on f of x is equal to IH bar operating on f of x, and therefore we conclude that the commutator between x and p is equal to just a constant IH bar. Again, it's an operator. An operator being a constant means you just multiply whatever follows by that constant number, IH bar in this case. Okay, so that's one simple kind of operator. Probably somewhere in the homework I have you calculate a different commutator. So we'll practice with that a little bit more. My notes indicate that I have some sort of voting question here. We just found out that I didn't put hats on these operators, but if usually, and I think Griffiths puts little hats anywhere there's an operator, so these should really have hats on them. If the commutator between x hat and p hat is IH bar, what's the commutator between p hat and x hat? Is it IH bar, yes or no? Okay, let's see a vote. It's unanimous. The noes have it, I think. I didn't see Alvis's, but everybody's saying no, and that's because of this minus sign here. Notice that if the commutator between A and B is this, that means, I'm going to sneak something in here, the commutator between B and A is B hat A hat minus A hat B hat. And notice that's the exact negative of what this one is. So when you switch the orders, you get a minus sign. Commutator between A and B is the negative of the commutator between B and A. So the correct answer here would be minus IH bar for that second commutator. Okay, commutators aren't too bad to deal with. It's just unfamiliar. They're sort of unfamiliar language, and so you have to learn to practice with them a little bit. All right. Now, why are we talking about commutators? Because we're going to do some algebra specifically with these A plus and A minus operators, which are built out of X's and P's, so it's not too terrible. Oh, sorry about that. So it's pretty easy to check in terms of the definitions of A plus and A minus that I've got up here on the board, that when you multiply A minus times A plus, of course, you know, there's a lot of stuff. You really got to do the details here. But if you multiply A minus times A plus, you're going to get something like a P squared. Turns out you get a P squared over 2M, right? And then you'll get something involving M omega, and this is an X, right? Just means multiply by X. So you're going to get something involving M omega X. And when I multiply that by another similar one over here, the A plus times the A minus, I'll get something involving X squared, which is like the potential. So you can show, it's just a matter of working it out, that when you substitute in the definitions of X hat and P hat into these and put them next to each other, what pops out is the Hamiltonian. That means P hat squared over 2M, or minus H bar squared over 2M D squared dx squared plus V of X. All of that divided by H bar omega plus 1/2. There's nothing complicated about it. It's just a matter of foiling it out when you put these things next to each other, an A plus and an A minus, or I'm sorry, that was an A minus and an A plus. And similarly, if you put them in the opposite order, A plus, A minus, you get almost the same thing. Same Hamiltonian divided by a constant, but you have a minus 1/2 instead of a plus 1/2. And we're going to use those in just a second. That also, notice that that means we have two expressions we can derive for the Hamiltonian. I could solve this for H, and this is an expression of H in terms of A minus A plus operators. This is an equivalent expression for H in terms of A plus followed by A minus. And we're going to use those later on. Okay, I know they're unfamiliar, but the idea is, hey, if I put in the A plus and the A minus and I simplify everything, you'll see I get my usual old minus H bar squared over 2M D squared dx squared, all that kind of business that usually is in the Hamiltonian. Okay, so I didn't show this, but I claimed that you could easily show that these two things are true, written there. Given that those are true, what's the correct expression for the commutator between A plus and A minus?
I'm just going to be a smart aleck and answer A.
Okay.
No, I'm just kidding. I'm just kidding.
Yeah, that may vary by who's answering too, you know. I'll give you a hint. It's not too complicated to do in your head. It would be maybe for a non-physics major, you know, someone who has trouble keeping a couple symbols in their head, but here it's just a matter of understanding what that commutator is in terms of those products given above. All right, let's see a vote on that and see if we agree here. Okay, I'm seeing all D's in the classroom here, and I agree, it's -1, right? When the definition of this commutator is A plus A minus, which involves a -1/2, and this Hamiltonian thing up in front, minus A minus A plus, so we get a -1/2 there, and these things have opposite signs, so they cancel out, but we get a -1/2, -1/2, which is -1 there. So the answer is D. Any questions on that? This is all going to be used in a proof that we're going to do shortly. Okay, so what that means is, yeah, this is, I know I chose the opposite convention here, but the one we just proved was A plus A minus commutator. Here, for some reason, I've written it as the commutator between A minus and A plus. I switched the order, and so of course it's +1. The other one was -1, just when you switch the order. And therefore, I can conclude something about if in an algebraic statement I have an A minus followed by an A plus, I'm welcome to replace it with A plus and A minus, but I have to pay an additional penalty by adding 1 there, right? So instead of just willy-nilly switching the order of things, you can switch the order, but you got to add 1 to the switched order. And same thing if I'm switching them in the other direction, there I have to subtract 1. Those both come out of this commutator by solving for this one or solving for that one. Okay, we're going to use that. That's just called doing algebra with operators that don't commute. Here's the central claim that we want to prove that's going to, from which all of this useful stuff is going to follow here. Let's suppose we know a solution to our time-independent Schrodinger equation using the harmonic oscillator potential. And what that means is that H applied to that psi is some E times that psi. What we want to show is that if we take, instead of just psi, A plus applied to psi, then when we hit that with H applied to A plus psi is going to be E plus H bar omega times that same thing, A plus times psi back again. And there's a similar relationship for H applied to A minus psi is E minus H bar omega times A minus psi. Okay, let's see if we can prove that. We're just going to start with the top left statement right here, okay? So let's start with H, A plus being applied to A plus psi. And what I'm going to do is immediately use one of those two expressions for H that, you know, I didn't show all of the details there, but it's not hard at all to show that this is a totally valid expression for H hat. Maybe what I'll do is kind of go around the room and throw Alvis in there at some point, and I'm going to make a transformation, one step of a transformation. I want you to tell me what's going on from one step to the next. What happened here between the first step and the second step? Mackay, maybe. Yeah, I just distribute the A plus in from the right. Now you have to be careful when you do distribution, right? It matters the order of operators, so that if I'm distributing this A plus onto the 1/2 and onto this stuff, I've got to keep it on the right-hand side. I'm not free to just move it to the left-hand side of a bunch of operators, right? It's got to stay in the same position. But you can distribute from the right or to the left. When I distribute from the right, I've got to make sure that my operator stays, when I distribute from the left, it always has to stay on the left when I distribute it. And same thing when I distribute from the right. So all I did was bring that A plus into the parentheses, which was part of the Hamiltonian operator. Okay. Riley, can you inspect the second to the third line and tell me what happened there? I factored out the A plus because I noticed up here, I've got an A plus on the left-hand side, and that's one case where it's okay to factor it out to the left. And this one, it may as well be on the left. There's no other operators there. So I can factor that out on the left. Okay, good. Nothing complicated. All right, what happened here in this next step? Alvis, you want to look at that one, and can you inspect it and tell me what goes on from the third to the fourth line?
Oh yes. So you add 1/2 in order to get to 1, and then for the sake of consistency, you then subtract 1/2.
Yeah. Do you have any idea why I might be, that's certainly true. This 1/2 is equal to 1 minus 1/2. Why would I want to do that? What am I trying to construct over here? And why did I show you these expressions that suddenly appeared up there? Anybody can tell me that? Jake?
In order, oh.
Right. I want the Hamiltonian to kind of appear over here. Before we had an A plus A minus version of the Hamiltonian. That's the lower one over here. Now, after doing this business, we'll see why we're doing all this in a second, but I want to rewrite this in terms of the Hamiltonian because we're going to use H psi equals E psi in just a second. So this is the Hamiltonian. I had a plus 1/2. I wanted a minus 1/2, and I'm welcome to change it as long as I add 1 in there. Okay, so I'm just trying to get the Hamiltonian back there. All right. What about here, Tanner, you want to look at this next step there? Yeah, what I did was, there's two sets of parentheses up here. Yeah, I just distributed the h bar omega onto these first two terms and then onto the last term, that third term. Okay, so that's really a trivial step. And Yi Chen, what's happening in this last step here? Yeah, one of our assumptions is that we've already found a solution. This psi is supposed to satisfy the time-independent Schrodinger equation. So H applied to psi gives some E times psi. I don't know what E it is, but we're calling it E. So here was H. That's appearing one of those boxes to the left. H applied to psi can be replaced with a simpler E multiplied by psi. So there we go. And once I do that, well, somebody tell me what's happening in the last one here, maybe Jake Fowler. Yeah, any operator always commutes with a constant. So constants can be moved willy-nilly around when you have a bunch of products, because our operators that we're talking about are all composed of functions of x and derivatives, combinations of those. And when you have a function of x and derivatives acting on a constant, the constant can just pass right through all the derivatives and functions of x. So I switched the order there. And then I put a check mark next to it because notice, we'll think about why we care about this in just a second. Notice that we've proved the first statement there, okay? And the second statement is no more or less difficult. We're doing the same things, but using different expressions. So I'm not going to bother you with asking you what's going on here, but I'm starting with the second one over here and replacing one of the versions of the Hamiltonian, distributing that A minus from the right onto the parentheses, then taking out an A minus on the left-hand side, right? And in this case, I guess I've skipped a step here, but this was the case where I replaced a minus 1/2 with a plus 1/2 and a minus 1 somewhere in here, right? When I factor that out, I would have a minus 1/2 left, and that's that's minus 1 plus 1/2, and there's the plus 1/2, and the minus 1 is multiplying an h bar omega. So same kind of stuff we did before. H is sitting right here. H times psi is E times psi. And then I can commute this constant with the A minus. Okay. Not scintillating. This just had an example of how to do algebra with operators, which we're not used to doing. You cannot ever switch the order of things, including when you distribute. If you're distributing something from the right, it's got to stay on the right, and you have to think about whether you can switch it with anything along the way. Okay, so let's think about the importance of that. I've just found out that so we started out by saying that we found some state, here it's labeled as psi n, but we just call it psi. H operating on psi is E times psi. And now we were able to show that H operating on A plus psi is equal to E plus H bar omega multiplying A plus on psi. What does that tell us? What's the best statement of the ones below about what we can conclude from that statement about A plus psi n? Let's see a vote on that. I'm not sure if you guys are ready to vote or you're still computing. you know, A sounds like more or less of a joke, so it's between B and C. All right, well, if you got a vote, hold it up and we'll just see. There's a little bit of disagreement. It looks like the B's are the majority, at least I didn't see. Alvis, is that a 2 you're holding up? Yes, okay. So the B's have it. That's not the correct answer in this case. It's not proportional to the state psi n. How might I know that, right? If, let's suppose that A times psi n, A plus operating on psi n, were just 7 times psi n. That's what B is saying, right? It's a stationary state because we already knew psi n was a stationary state, but it's just a multiple of it, like 7 times that same state again. What would that mean when we operate with h on 7 times the original wave function? Yeah, we would get the same energy eigenvalue back, right? If I have you know, what I'm going to say is not complicated at all, but sometimes when you're first thinking about this stuff, it makes sense to write it down. If I have an, you know, suppose an operator operating on a function of x gives 7 operating on that same function of x. And now I say, oh, I've got a new function, g of x, which is just 11 times f of x. It's a multiple of f of x. That's what B is claiming. And I let A operate on g of x. Well, g of x is just 11 times f of x. And when I let A operate on, so this would be A operating on 11 f of x, and the 11 can be moved out in front. And we know that A operating on f of x is 7 f of x. I sound like a robot. And in this case, wait, h, oh, that was an 11, okay. And then I have, that's equal to 7 times 11 f of x, and that's equal to g of x. Okay, so it's saying A operating on g of x would be 7 times g of x back again. It would have the same eigenvalue as the other function. Now let's go back to the slide, and this is what we've shown in this theorem. This is the punchline of the theorem. When h operates on this new function here, a plus psi n, that's some other function after a plus operates on it, we don't get en back again, or the same e back again. We get a different eigenvalue coming out, e plus h bar omega times that. And that means it can't be just proportional to the original psi that we assumed already was a solution. It's got to be a different, linearly independent solution. And that's important because we're looking for different solutions. So the answer is it's a stationary state, but it's not proportional to the state psi n because the eigenvalue is different. Proportional eigenfunctions have the same eigenvalue because the constant just goes along for the ride out in front. Okay, so here's the punchline of that theorem. In other words, if psi is an energy eigenvalue with energy E, then A plus psi is a linearly independent eigenfunction with eigenvalue E plus h bar omega. And A minus, operating on psi, is another linearly independent eigenfunction with a different eigenvalue, E minus h bar omega. And then if those are eigenfunctions, then we can apply A plus to them and do the same thing. We can keep going and going and going and get an infinite number of solutions this way. We're building up a ladder of solutions. Kind of amazing. We didn't even solve a differential equation at all in this case. We did it with algebra. That's why it's called the algebraic solution. Okay, so we just need one solution. We haven't found one solution, but we're about to get there. If we can get one solution, we can just keep going up and up and up and down and down and down, and we can get an infinite number of states, and we're just going to at least hope that those exhaust all of the available eigenstates. So it's just a question of whether they're complete or not. If they're not complete, then we're missing some of them. Now, here's a problem that I don't think I assigned anywhere. And maybe it's worth doing on the board just for a second. Problem 2.2 in Griffiths shows that there's always a time-independent energy equation solution. We'll call it psi 0, at least for the harmonic oscillator. For the infinite square well, the lowest energy solution was called psi 1. But traditionally, as you probably know, we call the lowest energy state psi 0 for the harmonic oscillator. There's always one of minimum energy. Here's the proof. You start with the time-independent Schrodinger equation. Maybe I'll share this again here. Okay, let's write down the time-independent Schrodinger equation. Minus h bar squared over 2m d squared dx squared of psi. That's kinetic energy, p squared over 2m, plus potential energy as a function of x operating on psi. Psi is a function of x, but I'm just not writing the function of x there, equals E times psi. I'm just going to recast this in a slightly different form. I'm going to solve for the second derivative because we're going to think about the concavity of this function, right? How much it's curving up or down. So let's solve for d squared psi dx squared. You guys can tell me if I make an algebra mistake here. Let's see, if I put that over there, I'd have an E minus V operating on psi. But then if I put the minus sign over there, I'm going to have a V minus E operating on psi. That's including the minus sign being put over there. And then I'll also have a 2m over h bar squared, I think. Okay. Now, so here's what problem 2.2 leads you through. And I don't think I assigned it, but it's pretty easy to actually do. Let's think about our potential energy. It doesn't have to be a harmonic oscillator potential energy, but if I plot V of x as a function of x, I'm just drawing a picture that looks like the harmonic. It could be any shape you like for the potential energy. I'm going to draw some potential that has a minimum value. In other words, it doesn't keep going down and down and down, and we'll see there's problems with potentials that keep going down and down. But if there is a minimum, the lowest energy state has to have an energy which is above the minimum of the potential. In other words, there's never going to be an energy eigenstate, a solution to this equation, where the allowed energy is below the minimum value of the potential. It's got to be at or above the minimum value of the potential. And why is that? Well, so let's suppose E is less than V of x everywhere. Okay, that's what we're trying to prove can't happen. So what I'm claiming is this kind of thing can't happen. This would not be an allowed energy. An allowed energy's got to be up here somewhere. And if it's got to be up here, there's got to be one that's the minimum because you can't keep going down, right? Suppose the energy were less than V of x everywhere. Then this is positive everywhere, right? If this is less than this, right? Let's draw a picture now of psi as a function of x. Let's suppose that we're in a region where psi happens to be positive. So here I am at this x, suppose psi is positive. If psi is positive, and we're assuming that E is less than V of x, the whole right-hand side is positive. And that means the concavity is positive. Okay, I can't see anything about the concavity, but you know, either it's on its way up. Positive concavity means, you know, sort of opening upward, where you're in that kind of shape, right? it's either opening like that, or maybe it's going down like this, right? If it's going up like this, we've clearly got problems because that curvature isn't, or the concavity isn't going to change. It's going to keep going up and up and up and up, and it won't be normalizable. When we take the magnitude of psi squared, there's going to be an infinite area under the curve over here. And similarly, if it's going down like that, that's a positive concavity, right? Then it's going to have an infinite area over on this side when we take the area under psi star psi. And therefore, it's not normalizable if psi is positive. Same kind of argument happens if, let's suppose psi is negative. Some point on the x-axis, psi has a negative value. Then the right-hand side is negative. If E is less than V, this is still positive. If we assume psi is negative, the concavity is negative. That means it's sort of curving in generally in this direction. And it's either curving down like that or it's curving like that. Those are the only possibilities. And one of those cases, this one right here, when we take the area under psi star psi, after we square it, we're going to get an infinite area under the curve over there. And for this one, we're going to get an infinite area under the curve on this side because it can't change. That concavity has to stay negative forevermore because this is I'm sorry, I'm losing my, because this is positive always. You know, I guess, you know, you could say, well, what if this comes up and it hits 0? Then it has to become positive by the same argument we made before. But we're still going to have the problem with this part of the function over there. And there's going to be a problem over here. So you can think through the details. But the assumption that E is less than the minimum value of V is impossible because an eigenstate's got to be, energy eigenstate has to be normalizable. And we've exhausted all the possibilities. They're not going to be normalizable. There's no states with E less than the minimum value of V. And so the claim is there's got to be a minimum energy eigenstate, right? All the allowed energies are up here and they can't go past there. So let's just take the smallest of those. There's going to be some minimum that happens there. That's the upshot of what I was just saying. Any questions on that? Proof? I could have assigned that problem, but it's pretty easy to just do here in class. So there's going to be some stationary state, time-independent Schrodinger equation state that has minimum energy. And for the harmonic oscillator, traditionally we call it psi 0. In other words, we call E0 the lowest energy. Now, if that's the lowest one, it seems like we're in trouble because we just showed, we proved a theorem that essentially said, well, let's consider the state A minus applied to psi 0. Whatever energy this state had, this one seems like it's going to have an energy eigenvalue that's less than that by h bar omega, right? If this one has energy E, psi 0, then this whole thing has energy E minus h bar omega, and we found a time Schrodinger equation solution with less energy. And that's contradicting the result of problem 2.2. So what's the solution to that? You know, you've done the reading, so maybe you know what the answer, the way out of this conundrum is. If there's a bottom rung of the ladder, we're talking about a ladder of states, if there's a bottom rung, which we showed in problem 2.2 has to be the case, and the energy we call E0 there, then what does A minus applied to psi 0 have to be? All right, let's see a vote. I know you guys are still thinking, but I see a few different answers being held up. Some both A and B, and then some up here in the A and B category. The basic answer is it's got to be 0. But there's a reason why A is also correct, and so therefore I'm sympathetic if you voted for D also, because notice that well, no, actually, I disagree with that. There's no A minus out there. Okay, so it's got to be 0. Why does it have to be 0? Because if I take A minus on that state psi, and it's equal to 0, what happens when I apply A minus, if it's 0, then notice I can rewrite 0 as E minus H bar. So let's assume that H psi equals E psi. Then if I take A minus times psi 0, that's going to be equal to, if it's 0, then if I apply H to A minus psi, that's still going to be 0. When you apply any operator to the 0 function, you're always going to get a 0 function back again. That's true for all linear operators. That's 0. But hey, can't I write 0 as E minus H bar omega times 0 back again? And this was our A minus psi. So it still satisfies the equation we said it had to. H being applied to this has this constant being applied to this. It's just that this isn't an allowed energy eigenfunction because it's not normalizable. So we don't get another rung down on the ladder from that lowest state because it's got to be 0. And therefore, there's that lowest state, which we're calling psi 0. So the answer here is, I don't know if I have it marked here. Yes, 0. For a second, I was thinking this said E minus H bar omega being applied to A minus psi 0. And that would actually be true if A minus psi 0 were 0, then A would be true. But since there's no A minus there, then that's not true. So the only correct answer is B here, I think. Okay, so almost through the logic here of this. Okay, so what we're going to do to figure out, remember, to get this ladder of states, we need to find one state, and this psi 0 is going to be the state that we find out. This is a differential equation in disguise. What we got to do is go grab the definition of A minus in terms of the momentum operator and the position operator, put it there, and put a 0 on the other side. And that's an ordinary differential equation. And what you're going to do now is solve that ordinary differential equation, just to take a little break here, as a worksheet problem. Find the correct one. Here it is. So let's do problem 1 on here. And Alvis, I believe these are under today's date on the website. This is the first of 2 worksheets. Oh yeah, I was thinking, where's Gracie? But there's a soccer miss today, is that right? I have a vague, Gracie's on soccer, I think, and yeah. I have a vague memory of soccer going somewhere today. So you can check if you want that when you take the definition of A minus from above, you get what's shown up there. But really what I want you to do is solve that differential equation. It's an elementary kind of differential equation that you learn how to solve in your ODE class. It's called a separable differential equation, if that means anything to you. If everybody's having trouble getting started, the first line is all important, let me know, and I'll just point you in the right direction. Oops, forgot my X there. And I forgot my dx too. So hopefully you're almost done now. Let me just remind you of, at least this is the way physicists, we could write it the way the mathematicians might do it, you would have done in your class. But the idea is put all this, with the way the physicists like to do it, is put all the psi's on one side and put all the x's on the other side, including the differentials. And I know that's, formally, we're not allowed to break up derivatives like that. They're not a ratio of differentials. But what we're going to do is do it anyways. And then later on, we can check that it's a solution if you want. And if it doesn't matter how sleazy of a method I used to find a solution, if I check it's a solution, it's a legitimate solution. So I put all the psi's on one side. And then what I'm going to do is integrate both sides. This side with respect to psi 0 and this side with respect to x. And of course, this is an indefinite integral, I've got to put a constant of integration if I'm doing an indefinite integral on both sides. So when I have d something over something, that's a logarithm, log of psi 0. I'll put the plus c on the right-hand side. And over here, I have a minus m omega over h bar. The integral of x dx is x squared over 2. So I'll write that as x squared. Let me put the 2 over here. And then I need to add a constant, and I could either add it onto the x squared, but all this stuff is constant. So there's got to be some constant added on to the right-hand side. I'm going to, combine whatever constant came from this with the constants out in front and call it c. And then the goal is to find psi 0. So we're just going to exponentiate both sides to undo the logarithm, use the inverse function. So that means that psi 0 is going to be e to the minus m omega over 2 h bar x squared plus c, all that in an exponent. And when you have a sum of exponents, you can write it as the product of the two exponents. And if c is some arbitrary constant, then e to the c is some other arbitrary constant. So we can put that out in front as our normalization constant, right? That's the a that we want to actually determine by saying that the area under this psi star psi curve is 1. you know, if you're a mathematician, you know, do this, you integrate both sides with respect to x, you'll get the same thing that way, and use the fundamental theorem of calculus over here. Integral of a derivative is the function. Okay. So, yes. So there's our solution, other than the fact that, well, I guess part of this was to normalize it, huh? And normalize it. So we got to normalize, oh man, I've got to do that Gaussian integral, right? So let's now figure out what A has to be. I'm going to require that the integral from minus infinity to infinity of the square of this, because it's all real, I don't need to worry about stars. That gives me an a squared e to the minus m omega. I just double the exponent when I square it. If I have an exponent like that. This is psi star psi along with the a squared. Integrate it with respect to x. And I've got to go back and see what my relevant Gaussian integral is. So for this form that's in the lower right-hand side, this is my a in that form of the integral. It's symmetric, so the integral from minus infinity to infinity is just going to be 2 times the integral from 0 to infinity, right? So this would be 2a squared times the integral from 0 to infinity of that stuff. And the integral from 0 to infinity, let me just write down what that result is supposed to be 1/2 times pi over a. 1 over a is h bar over m omega to the 1/2 power. Okay, and tell me if I've missed a constant here, and we're gonna require that that equals 1, and therefore figure out what a has to be. Okay, the 2 cancels the 1/2 there, and that means that a has to be m omega over pi h bar to the 1/4 power. If I didn't make any mistakes, let's go forward here again and see if that's, oh, I've got it there, yeah. M omega over pi h bar to the, looks like I have a typo there, huh? Is that a 1/4 or a 1/2? Kind of looks like a 1/2 to me. Should be a 1/4, it looks like. Okay. Hopefully that agrees with what's written in the book. I'd have to check my original handwritten notes, but it looks like a 1/2 to me. Okay. Now that I've got this function, so I know what a is, some annoying normalization constant, I can apply h to that and figure out what the ground state energy is. And when you apply h to it, you can just figure out that the ground state energy is, 1/2 h bar omega comes out in front of this when you apply h to it. Okay, so the ground state energy for the harmonic oscillator is 1/2 h bar omega. Question so far. I know this is it's a little bit of a beast, especially that we've never seen the algebraic solution before, but that's part of what we're learning in quantum mechanics is not just solving differential equations, but sometimes thinking of the algebra of operators. Okay, I know this is a little bit of a blurry scan, but it's from Griffith's book here. So this is the notation you'll see in the book, but same thing. Here's our psi 0 up there. Here is the lowering operator, I think, right? There is the raising operator, and what we're going to do shortly is calculate. We found out that if I know a state, and I now do know one state, what I can do is apply a plus to it. I can't apply a minus to it because we already know we required that that's 0. It's the minimum energy state. That gave us our differential equation. But we can get a new state by applying a plus to psi 0. And we're going to call that the state psi 1. That'll be the next allowed energy there. Okay, so let's do that. And this is the worksheet on the backhand side. And I kind of decided that, after doing problem 1, maybe we could just talk through this one together because it's a little bit more of a mess. And I guess I should also say that Griffiths writes these not in terms of x, but a lot of times in terms of this Greek letter xi. You know, it kind of looks like a squiggly E kind of thing. Xi is defined as the square root of m omega over h bar times x. So xi is proportional to x. And it just simplifies the formulae a little bit to write it in terms of xi rather than x. All right, so let's apply a plus to psi 0. Here's our expression for a plus right here. Just pulling the definition from before, and here's our psi 0 that we just worked so hard to find out. I've got to take a derivative of this Gaussian function. Of course, when I do that, it's going to pull down a 2x with some constants and give the Gaussian back again, right? And then I'm also going to have another term that has an x multiplied by the Gaussian over there. So when I do that, both the derivative term gets an x out in front of a Gaussian, and this one also has an x out in front of a Gaussian. And so you'll find out it simplifies to that case there. And now, of course, this is a 2 times m omega x. And now I'm just going to try to simplify this function. Our goal is to say, well, this is a new eigenfunction. We might have to normalize it. The psi 0 was normalized, but there's no guarantee that this is the normalized psi 1. So let's now combine the m omega x's together. So they're starting at the same place again. And what I'm going to do is try to rewrite it in terms of the variable xi. I'll write it up here on the board because it's not written there. Xi is equal to the square root of m omega over h bar times x. And I have something that looks like a 2m omega x here. So I'm going to rewrite it in terms of the m omega x part, accepting the 2 that's sitting in front of it there, in terms of xi. Well, in order to turn this m omega into a xi, what I need to do is multiply by, let's see, maybe I don't want to do it in my head. So what I have is a 2 m omega x. And I want to convert it into something that looks like this. I want to write this thing as a xi. To do that, what I need to do is divide by the square root of m omega. And that's going to, when I do that, that's going to leave me with a square root of m omega, right? I've changed it, but I'm going to undo it by multiplying by the reciprocal out in front in just a second, right? And I also need to divide by the square root of h bar. So what's left here is now exactly, the x is still coming along for the right. This is exactly xi. And I'm allowed to do that as long as I also multiply by the square root of m omega h bar, now that I figured it out. And that's what's happening in the next step there. I multiplied by square root of m omega h bar, and I divided by it, and then I simplified in terms of xi. And now all that's left to do is simplify the constants. Let's see. M omega over h bar times x squared is the square of xi. So this is minus xi squared over 2 in the exponent. And now the constants out in front, there's a root h bar in the numerator and denominator, and you can combine together the pieces. And this, it just keeps piling on worse and worse. The 2xi is known as the first order Hermite polynomial. It's a polynomial as a function of xi. The one, you know, whenever you see these subscripts, so it's a Hermite polynomial, that's what the h stand for. The subscript tells you the order of the polynomial. This is a first degree polynomial, right? It only involves highest power of xi to the 1. So that corresponds to h1 of xi. So Griffiths writes it that way. And Again, we're not guaranteed that this is normalized, so you could go ahead and try to normalize it and you find out it's already normalized. There's no guarantee that that was true, but if you compare to the normalized versions that are in Griffiths, this is normalized. So when you integrate from minus infinity to infinity of psi star psi, right? When I do psi star psi, you probably want to do it in terms of x, but right, I would have one, since this is proportional to x times e to the minus something x squared, when I do psi star psi, I'm going to have x squared times e to the minus something x squared, and you could use those integral tables for the Gaussian, powers of x times Gaussians and figure out what the normalization constant has to be. And this is exactly it right here. So it's normalized right there. What does that function look like? Well, it looks like a Gaussian function, right? This is e to the minus something x squared. We know that looks like a Gaussian, so, and with a constant out in front. So here's the picture from Griffiths. He's showing the potential as a function of x as the parabola. And then on the same picture, he's showing what the shape of the wave function is for the ground state. And it's just a simple Gaussian. Over here is the corresponding probability density. When you square a Gaussian, it still looks like a Gaussian, right? It actually is a Gaussian, it's just a different Gaussian. Okay, so that's what the ground state looks like. I'm just going to take a quick look at my notes, make sure I'm not passing over anything here. Okay. Let's keep going here. Griffiths likes to use this, and this is traditional in the mathematical physics literature. Instead of using x, because this combination of constants appears everywhere, everything just simplifies if you write in terms of the Greek x, xi. Okay, and you can keep doing that, right? It becomes increasingly a pain to apply a plus to the previous one and get the next one. But what you would do is take your psi 1, apply a plus to it, and that's proportional to psi 2, and then you normalize it. And Griffiths has done all the work for us here. He keeps going up, and this is what results. This is the formula for all the psi n's starting at n equals 0. N equals 0 is the ground state. Traditionally, we label the ground state with a 0 index there for the harmonic oscillator. So what they are, ignoring is just a huge constant out in front. Okay, so that's a normalization constant. So what we have is a polynomial, that's what the Hn is, it's just some polynomial of xi, and xi is proportional to x, so you can think of this as a polynomial in x too, times a Gaussian, e to the minus xi squared over 2. Here are the polynomials. The subscript of the h tells you the degree of the polynomial. So h4 is a 4th degree polynomial, and interestingly enough, they always are either all even or odd powers of xi in there, or x, if you write it in terms of x. Okay, those are called the Hermite polynomials. All right, this is a little bit of a non sequitur here, but part of what we're seeing here is that our wave function keeps staying non-zero even for parts of the potential where the potential is huge. Right? Here on this same diagram, so this is v of x. This is the corresponding e, this horizontal line. And notice it's above the minimum of v of x, so it's a perfectly allowed state. But the wave function is still non-zero, 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 all the way off to infinity. It stays non-zero. And that doesn't sound like something that happens classically. So what I'm asking here is, on the next voting question, we're going back to classical physics now. Particle in a quadratic, energy potential. Or not even that, doesn't have to be quadratic, any potential. What's true about that particle and a region where the energy is less than the potential energy? So we're talking about I've got some potential energy, my particle might have a total energy, right, which is being trained, here it has a lot of potential energy, but less kinetic energy. But, the total energy is the same, as it goes back and forth in this potential well and oscillates like that. What would you say is true in classical physics in a region where the energy is less than the potential energy? Let's just see a quick vote. I'm seeing some people already voting. Yeah, the fingers I'm seeing are, or cards are all for A, the particle can never be there. That's right, it's called the classically forbidden region, right? In this case, if my particle has total energy, E, it's gonna stop and turn around, and its oscillation will look like this as time goes on, right? It can never be in this region because it would have to have negative kinetic energy to make up for the really large potential energy, and you can't have negative kinetic energy. 1/2 mv squared, those are all positive things, so they can't end up being negative. So it's classically forbidden. Now, comparing to quantum, what has to be true for a quantum description of a particle with energy E in a potential V of x? Same kind of picture, right? But now we're not thinking of a point particle moving around, but we're describing that point particle as one of these waves. What has to be true in a region of the wave function, in a region where the energy of the particle, this perfectly allowed state because its energy is above the minimum of the potential energy. So it seems like there's nothing wrong with it. But there is a region where that energy is below the potential energy. What has to be true of the wave function there? Okay, let's see a vote. Some of you were still thinking a minute ago, but the C's have it in terms of the vote in the room. It can be non-zero there, but it's got to get smaller with increasing x. That seems appealing, and there's, you know, that certainly is something that can happen, but D is actually what, you know, what in general can be true. It can actually get larger with increasing x or get smaller. In other words, here's the situation. Let me draw over here where Alvis can see. Let me show you a particular kind of well that people have told me you did in modern physics. The double well, you know, as a well with sort of a bump in the middle. So it looks something like this. Okay, that might be a polynomial that's fourth order or something like that. It could look like that, right? And let's consider a state. If this is sufficiently tall, there's going to be a ground state that is certainly above the minimum of the potential energy. So it seems like an allowed maybe ground state for this. But it is in this region right here. That's the classically forbidden region. What has to be true of the wave function there is that, right? So it's got to be, as I'm going deeper and deeper into the region where the potential energy is greater than the energy, the amplitude of the wave function, if I imagine plotting the wave function where this is like my x-axis, the amplitude of the wave function has to be getting smaller, but then it gets bigger again. In other words, it has some non-zero amplitude over here and has a non-zero amplitude over there. And so it's got to get bigger on both sides. Maybe it'll make more sense if we write down the Schrodinger, time-independent Schrodinger equation. Let's write it down in terms of the second derivative. Of psi with respect to x. Can I remember what goes on this side? 2m over h bar squared times v of x minus psi. Psi minus e times psi. Now let's just think roughly for a small region, if we consider just a small region on the x-axis where v of x is almost constant, and let's take a region where E is greater than v of x. If E is greater than v of x, that would be like in this region. If E is greater than v of x, then this is negative. And I get a differential equation that looks like The second derivative is a negative constant times that function back again. That's your harmonic oscillator differential equation, right? So you're saying in a small region where v of x is approximately constant, this is going to be approximately constant, and therefore this is just one big negative constant there if E is bigger than V, right? If E is bigger than V in that region, it's a negative constant. And that looks like d squared psi dx squared is minus k squared times psi. It's going to oscillate there. So we're going to find out in this region here, the wave function is oscillating. We're interested in the other cases. What if this ends up being positive? That would be a case where the energy is less than the potential energy, like it is here. And if that's positive, you're going to find out that this actually, instead of oscillating, it's monotonic. In other words, its second derivative keeps going the same way. So it either keeps curving this way or it keeps curving this way. Now, one way, some of you or many of you voted for, I think it was C, whereas the correct answer was D. So let's, can go back to our quadratic potential like this. And let's imagine we're considering a state that has, a stationary state that has that particular energy. So over here, it's in the classically forbidden region. We've just found out that, if this is the ground state, and I draw it as if this is its x-axis, or then the ground state solution looks like this. We said the concavity, if it has a positive, if psi has a positive value, then the concavity has to be positive, right? If this is positive, then if we assume psi is positive, then the concavity has to be positive, and it is positive there, right? So it going to zero or getting less and less is one way for it to do that. And similarly, as we go to negative infinity over here, but we're also going to find in cases like this is still valid, right? This thing right here, if we assume it's positive and psi is positive, as I've drawn right here, then the concavity, all we know is that the concavity's got to be positive too. So it can go down or go up. And we'll see cases where it does go down as you go to the right or go up as you go to the right. Of course, once you get deep into negative territory, it's got to keep going down to zero in order to be normalizable. But in middle regions, that's not necessarily true. I don't know, maybe that was like somewhat confusing. That was to have that conversation sort of in general, and it connects back to what we talked about there earlier, thinking about the concavity of the wave function. So the correct answer there is D. It can either get smaller or get larger, but if psi is above zero, the concavity's got to be positive. If psi is below zero, the concavity's got to be negative. And that allows for cases where it goes to zero, but it also allows for cases where it seems to be getting bigger on both sides, and it is getting bigger. Eventually, it's got to get smaller over there to be normalizable. Yeah, what were you going to say, Jake?
I would say that's like, obviously in this case, that hump is in the middle of a well, but if it was just that hump, like, we're just like, in the case, I'm just like recalling from Potter stuff that in the past.
So what are you thinking of altering here? Is the
Like-
potential energy the same here?
No, like, it's just, like the timeline situation where instead of looking at a well, like, it's just.
Yeah, so a typical tunneling kind of potential might look like this. So that's our V of X. And you start out with a state that, it's not going to be an energy eigenstate, but if I start out with a state that is maybe a Gaussian function that's centered in this region, I will find that as time goes on, more and more probability leaks out over here. And this hump, as time goes on and we solve the time-dependent Schrodinger equation, this hump gets smaller and smaller, and you get a larger amplitude out here that kind of spreads off towards infinity. So go on with that.
Then I was just like discussing this case, like, it was still.
Yeah, so in this case, in the case where you're discussing tunneling like that, this is not an energy eigenstate. I know. What about my discussion that I just had tells me that this cannot be an energy eigenstate or a solution to the time-independent Schrodinger equation that I drew right here. Like if I say as time goes on, it leaks out over here. That's called tunneling. Because let's suppose we knew the energy was somehow so that it made it forbidden to go over there. Then it shouldn't be able to get past this potential hump there, and yet it sort of leaks out if we follow the time-dependent Schrodinger equation. How do I know the state that I talked about starting with is not an energy eigenstate? What has to be true of the probability density for an energy eigenstate as a function of x or as a function of any variable, but here I'm thinking of as a function of x. Its total integral is 1, and that's true for any state, even ones where it leaks out. But another name for an energy eigenstate is a stationary state. Stationary means the probability density can't change with a function of time. So as time goes on, some probability is leaking to the right. Oh, that's not stationary, right? When you look at a stationary state and you solve the time-dependent Schrodinger equation, the shape of it should just stay still. It doesn't change. The probability density stays the same as a function of x. So this kind of thing that is going to leak out is not a definite energy state. It's got to be a linear combination of definite energy states, which is itself not a definite energy state. Yeah. I'm not sure what you mean by physical waves. Are you going back to what we talked about in chapter 0 or? Well, the best way to think about it and connect with what you know is to think about, well, in what limit would it connect up with classical physics, right? Because, if I have a macroscopic object and we think, technically a macroscopic object should be able to be described by quantum mechanics, but its description in quantum mechanics should sort of reduce down to what we know from classical mechanics in a certain limit. Now, if I have a ball, going back and forth in a potential energy well, it's got a macroscopic mass, so it's got some huge momentum that's switching back and forth as time goes on. That's not going to be close to the lowest energy state, right? Even if I could put it in a definite energy state, its quantum number is going to be astronomical, right? If we're talking about psi 0 and psi 1, psi 2, maybe we're talking about psi 1 million would, even that would probably be too small to be a macroscopic thing, but it would be some huge quantum number that would correspond to that. And so we ought to, I'm going to skip ahead of a voting question there and go over here and just talk about what happens as n gets larger, because Griffiths has a nice picture in his book. Just checking the time there. So we're still off by an hour. I guess we're on, must be on mountain time or central time, yeah. So here is a picture of psi 0. You know these before. This is psi 1. It's got 2 humps. Psi 2 has 3 bumps. Psi 4 has 4 bumps. And these are the probability densities over here. So we've taken the magnitude of psi squared, and you get 1 increasing bump. Now, if we're talking about a macroscopic kind of state, it should be some huge quantum number, n, not 1, 2, 3, or 4, but maybe a million. So Griffiths, just to sort of show the connection, this is psi 100, magnitude squared. So this is the probability density for psi 100. Now notice psi 4 has 4 bumps. Psi 100 is going to have 100 bumps. And that doesn't seem to look much like a probability density from classical mechanics. But we thought about, on one of the first days, when we were talking about chapter 1, if we had a ball that was rolling around in a gravitational potential well or oscillating in a some quadratic potential energy kind of situation, so it's oscillating back and forth, and we drew its probability density, we decided that wherever it's going to go slowest, it should have the largest amplitude, right? So if we release it from here, its total energy would be like at this height, right? And it has more kinetic energy but less potential down here, and then less kinetic energy but more potential, and it would oscillate back and forth. And we decided its probability distribution better be 0 in the classically forbidden region And then it's really large where it's going slowly, and it goes down, and then it gets really large where it's going slowly, and then it has to go down to 0 on the classically forbidden region. Now look at psi 100 here, which is supposed to be sort of like heading towards a macroscopic case. A large quantum number should correspond to what we understand classically. So this is as close as we can get in quantum mechanics to something that has macroscopic levels of energy. Well, it's oscillating very quickly. And if you're at the macroscopic level and you're not paying attention to things that are happening at very small scales of x, you might just say, look, it's going between a value and a 0 and a value and 0. We're just going to see it as kind of on average being halfway between the maximum and the minimum. So this dashed curve right here is if you can't pay attention to things down at the nanometer scale or something like that, you're going to just say, well, you know, the average potential energy is what I think the potential energy is in there. And notice it has that shape, right? It's minimum in the middle, and then it goes up, and then it heads almost instantaneously to 0. As you go to higher and higher quantum numbers, the speed at which this goes to 0 in the classically forbidden region cuts off faster and faster. So as you go to n equals 1 million, it's going to cut almost immediately off to 0 as you go into the classically forbidden region. And so that sort of connects a little bit with what you know from classical mechanics to what we're talking about in quantum mechanics. I'm not sure if that answered your question enough. Yeah. So think about, you know, when I talk about these things in class, that doesn't mean there's enough time to really digest this, but this is from Griffiths. So check that out. You can see the trend here. And this is way up when you go to n equals 100. Think about why, you know, we wouldn't notice the small scale variations in potential energy, and therefore we would just think of an average potential energy kind of halfway between. And it looks like what we did on that first day of chapter 1 for what we intuitively expect the probability density to be. All right, so let's look at this same simulation that I showed you before, which we were looking at the infinite square well, but it can do other potentials too. So this is still the infinite square well, but let me turn some things off so there's not so much being shown on here. And let's go to the harmonic oscillator. There it is. I mean, I guess the first, so this is showing the allowed energy levels. And one thing that's worth remembering is that unlike the case for the infinite square well, where the energy of the allowed, you know, the energy corresponding to the energy eigenstates, En was n squared pi squared h bar squared over 2ma squared. It's going up as the square of n. So if I plotted, you know, the allowed state energies, you know, here's the ground state. It's some fine, you know, it's pi squared h bar squared over 2ma squared. They keep getting more farther and farther apart as you go up in n because of that n squared effect, right? They keep getting bigger, faster, and bigger, faster. That's not true for us here. So we just showed that the ground state energy is 1/2 h bar omega. And we also showed that the first excited state is h bar omega up in energy from it. And the second excited state is up by h bar omega from it. So we would have 2 of those and so on. The correct formula when we put that together is, as you know, you should ring a bell, n plus 1/2 times h bar omega. But what that means is, as you look at adjacent energy states, you always keep going up by the same amount. So all those energy levels, amazingly enough, are equally spaced. So here are the allowed states, and we're going up to a very large state, not 100, but maybe we're at 15 or so by then, right? And here's something that's kind of interesting that Griffiths points out. So this is a stationary state, and of course its probability density doesn't change as time goes on. There's one that corresponds to n equals 0, 1, 2, 3, 4. N equals, no, it looks like n equals 5 that I've clicked on. And of course it has 5 bumps. This is a probability density. Remember that the fast changing colors are supposed to represent what the phase of the wave function is as a function of position, but the probability density itself is not changing. We could turn that off there. Whoops. I want to move this down, but I moved it up in the window and now I can't get it down. How can I do that? Well, in any case, I'm going to put it in the ground state there. And now what I'm going to do is add on to the ground state a little bit of first excited state. Okay, so I'm going to put it in a linear combination of the ground state and the first excited state. Of course, it's not in an energy eigenstate. That means it's not in a stationary state. And so we see the probability density moving. And it's behaving somewhat like, very loosely, like a ball would, right? The probability is sloshing to one side and to the other side, just like a ball would move from one side to the other side. And Griffiths makes the statement that this is true not for any linear combination of states, but if you take a state, so here's a very high n state. Let me clear this. I'm going to put it in kind of a high n state. And the probability density, which is kind of flashing in an annoying way, is at least not changing as time goes on. Its colors are changing, but the probability density is not changing. If I put it in a linear combination of that state and the next highest one or the next lowest one, so let's go one up from there. Again, it oscillates back and forth, and you can show pretty easily that the oscillation angular frequency is the classical angular frequency. So if you take a linear combination of two adjacent energy eigenstates, the probability density will oscillate up and down with the classical frequency that a ball would go back and forth with if it's in a quadratic potential energy function. That's another kind of connection. It doesn't even have to be an high n for that to happen. That happens between the, well, let's clear this again, between the first and the second. Oops, clicked on the wrong one. First, and there's the second. So that's a linear combination of the first and second, and it's oscillating back and forth with the classical oscillation frequency. Okay, so let's do now another worksheet. And Riley's got to go, unfortunately, but I'm going to give you a copy of the worksheet to take with you. Otherwise, I might forget it next time. This is to practice with doing the same stuff we've been doing with the infinite square well over and over again, but using this not so appealing function. I mean, it's still not so bad. It's polynomials times Gaussian functions. All of the psi n's have the form of a polynomial times a Gaussian function. And here you're going to find, even though we could find C1 and C2 and C3, I'm giving you a psi at time t equals 0. We first want to normalize it. That's nothing new. I just keep forcing you to do the same things over and over again. So hopefully it sticks, especially by next week's exam. Now we want to write that psi of x and 0 at the top as a linear combination of the psi n's, where the psi n's are these new stationary states for the harmonic oscillator. And they have the formula that's given here, which you might say, blah, it's written in terms of xi, but you could replace the xi in terms of x if you really wanted to. And the allowed energies are given there. Write down a formula for Cn, but it involves an integral. You don't have to do the integral because you could do the integral for C1 or C2 by integration by parts a few times, but it's sort of unpleasant to do. So we'll just leave Cn as an integral and think, I could do each one of those integrals for each n, but I'm not going to. And Alvis, you see this worksheet on the same date? This is the second worksheet that was posted next to the previous one.
Let's see.
Second worksheet for
Here we go.
today's.
Chapter
date.
2, suppose that a particle of mass m. That one?
Yes.
Excellent. All right. Let's see.
Mm-hmm.
I thought you showed that the lowest energy is 1/2 bar omega, right?
Yes.
So would n start at 1 or 0?
N starts at 0. And it's just a different kind of annoying convention difference between the harmonic oscillator index conventions and the infinite square well index conventions. And you'll see for some kinds of problems, we start at n equals 0 and some for n equals 1. But here, n equals 0 is the lowest. Oh, you're saying I have a mistake in my summation there. Yeah, in part B, there is a mistake in my formula. I didn't notice that. Psi of x and 0 should be able to be written as a linear combination of the harmonic oscillator psi n's, but these start at n equals 0, and so my summation index should start at 0 here, and I have it written as 1. That's a mistake. So the normalization constant here should be 1 over the square root of x0. In other words, that's how high it should go up to instead of 1, right? So we need to multiply that 1 times 1 over root x0. That's A. Okay, let's talk about this stuff together because, in this case, I'm not requiring you to do so much of the integrals because they're just kind of a pain to think about. If you look at them in detail, excuse me, you'll realize that you really could do each for C5, you could do that integral individually, but it would be a huge pain. So let's just look at it. Any questions on the normalization stuff? That should be old hat by now. So let's look at B. B should correctly say, let's write psi, this particular psi as a function of x at time t equals 0 as a linear combination of the psi n of x's. The sum has to go from 0 to infinity. We can't leave out the 0th one or it's not a complete basis set of functions for our infinite dimensional vector space. And the claim was always Cn can be calculated from the integral from minus infinity to infinity of psi of x and 0 times psi n star dx. That will give me a formula for Cn. So let's try to plug in what we know. It's kind of a mess. Psi of x and 0, let's see, that function is only non-zero between 0 and x0. So that means I can reduce the range of integration to there. And in that region, psi of x and 0 has the value 1 over the square root of x0. So that takes care of this part of doing it. Now I just got to put that next to psi n, which is kind of a mess. So that has an m omega over pi h bar to the 1/4 times 1 over the square root of 2 to the n times n factorial. Does everybody know what factorial means from some math classes, right? 5 factorial is 5 times 4 times 3 times 2 times 1. That's the normalization constant times the actual functions of x, which are hn of xi. I'm just getting, so we can write things as a function of x. I'm going to write xi as xi is the square root of m omega over h bar times x. So hn with that thing plugged in everywhere there's a xi times e to the minus xi squared, which is m omega over h bar times x squared divided by 2. So that's e to the minus xi squared over 2 if you plug in what xi is there. And so I've got to do this integral with respect to x. 1 for n equals 0, 1 for n equals 1, 1 for n equals 2, and those successively would give me all the Cn's. Now, most of this junk is just constants, right? All this stuff can go out in front of the integral. And what I'm left with, well, let's see. If I do the 0th one, h0 is just 1. So for C0, this becomes 1, and I'm just integrating a Gaussian, which I can do from the tables. C1, again, all this is constants, goes out in front of the integral. H1 is just this thing by itself. It is xi. So this becomes this. This constant can go out in front, so I get an x times e to the minus a x squared. And I can do that from the integral tables that you know too, right? Integral from 0. Oh, actually, you can't do them from the integrals tables, because I should say, we won't be able to do it analytically because our integral tables are only from 0 to infinity or minus infinity to infinity. We don't know how to integrate from 0 to x0, so we would have to do these numerically. And in fact, generally that the antiderivative of a Gaussian function is not an elementary function. It's a non-elementary function called, I don't remember if this one is the error function or the complementary error function, but it's some function defined in terms of an infinite series. But there's no convenient way to express it in terms of normal functions that we're conversant with. And so I'd have to do these numerically. But if I put in the explicit functions, I could go to Wolfram and get decimal approximations to each one of those as needed. Okay, that's B. C, that's the best I can do without actually completing the integrals. C, write down the formula for the normalized psi of x and t. So that's just saying plug in to this. And we're told, hey, I know you couldn't get a nice formula for Cn, so leave the Cn in there. So my formula for this would be, that's a lot of repeating the writing I already did. Cn, which is defined by this integral, times psi n of x, and psi n of x is that thing to the 1/4 power times the 1 over the square root of 2 to the n factorial times hn of c times e to the minus c squared over 2, and you could rewrite c in terms of x if you really want to. That is psi at x0, and then we know we're asked for the time-dependent version here, right? Not just the initial condition, but how does it wiggle and jiggle with respect to time? And we know what we do is in each one of these terms, we just add a factor of e to the minus I en t over h bar. And I know explicitly what en is now. So I'm going to put that factor multiplying the appropriate psi n here. So times e to the minus I en is n plus 1/2 h bar omega e to the minus I en t over h bar. And when I divide by h bar, it gets rid of that h bar that's there. So that's kind of as explicit I can get without putting the CNs in, without having a nice formula for CN. Questions so far? Finally, write down a series expression for the expectation value of the total energy. And we have two choices here, and we're allowed to use CNs. I'm going to erase my CNs, but we have kind of a messy formula for CN. The expectation value of energy, we could either go back to square one and say, well, that's the integral from minus infinity to infinity of psi star of x and t times h hat for the harmonic oscillator times psi of x and t, integrate with respect to x. And that's going to be a huge mess, right? Psi by itself is a huge mess. There it is up there. And I got to put a psi star in there and sandwich that. Oh, God, I don't want to do that. But we already showed there's an easier way. If you work out the details and use the fact that h times lowercase psi equals e times lowercase psi, we showed already in one of the previous worksheets that this can be written as the sum from 0 to infinity magnitude of Cn squareds. Griffiths tells us these are probabilities here, times En. Okay, so if I'm allowed to use the symbol Cn, I could just write this as n plus 1/2 h bar omega. And that should be the expectation value of E, if I could get the Cn's as individual numbers. All right, I think that's a good time to stop. Any questions? All right, that was a lot, but we're pretty much finished with the harmonic oscillator discussion. I should say, Griffiths goes into the analytic solution. We're not going to talk about it here. It is, you do something that you might have done in differential equations where you guess a series solution and you get a recursion relation for the coefficients in your power series, right? In a series solution, you say, let's assume the solution can be written as a power series, and then you get a recurrence relation for the coefficients in there. And Griffiths goes through that to some degree, probably not enough that you could easily reconstruct it, but with some difficulty, you could go through the details and show you get exactly the same psi-n's back again if you treat it as a differential equation. It's not so elementary because you have to, assume some asymptotic behavior, factor out asymptotic behaviors. Probably isn't something you did in Math 360. All right. I'm going to go to a meeting in a second, so unless anybody has a very quick question.